I'm on the group that helps organize these events. So before we get started, I want to remind everyone to turn off their electronic devices that might make noises in the middle of the lecture. Put them on vibrate or whatever other kind of feeling you'd like to get out of them. Or just silence them altogether. As I said, I'm one of the organizers of this event. These are this is the, I think, I'm going to say 57th, correctly, 57th of the Harry Kieval lectures. These are lectures that are given every semester since 1982, I think. Of course, in those days it was quarters. So it was twice, 2 quarters a year. And they were endowed by a former professor at HSU in mathematics, Harry Kieval, who since has left the room, as they say. So he used to come to these things even after he left the university, and he was living in Ashland, and he would come down to these things twice a year and visit with us and with the speakers that we would have. These are not the only Kieval lectures. Harry also endowed one a year at Southern Oregon University, where he was an adopted friend of the math department there. And he also endowed one of these at Cornell University, which was his alma mater. Besides endowing these lectures, Harry also endowed scholarship funds for our outstanding math senior majors. And if you are a rising senior math major, you might be interested in applying for that. Applications will be coming out in the next week or so for that scholarship, as well as other math scholarships. And with us tonight, I see is the current Kieval scholar, Jason McClellan, back in the back here. Jason, acknowledge you. So Jason's our outstanding senior math major this year. And the reason I stand up here at the front of the room is not to introduce the speaker, because we have somebody else to do that. I'm here to make some patter while people come in a little late. And I think we've reached that time when I should get off the front of the room and let our president of the University, Roland Richmond, introduce our speaker. So, Roland Richmond.
Thank you, Professor Flashman, and thanks to the mathematicians for inviting me to these lectures. I enjoy them, every one, and I appreciate the opportunity to listen to some mathematics. David Pengelley is a professor of mathematics at New Mexico State University, where he's been for some time. He recently, in December of last year, was named New Mexico's Professor of the Year, the whole state's Professor of the Year, by the Carnegie Foundation for the Advancement of Teaching. And one of the things they rewarded, and let me read a quote from his award, was his teaching method emphasizes student projects and advanced student reading, writing, and preparing mathematical work before class time, allowing for a non-lecture style. Moving away from lecturing is the most challenging change I have ever made, Pengelley said. I congratulate him for that. It's something many of us could do a better job of here as well, so thank you very much. He's received a number of awards, including the Heimo Award for Distinguished College University Teaching of Mathematics from the Mathematical Association of America in 2009, the West Haffer Award for Excellence in Teaching at New Mexico State University also in 2009. He received his bachelor's degree from the University of California at Santa Cruz. He spent a year, I presume, while he was getting his doctoral degree at Oxford University at the Mathematical Institute there, and got his PhD from the University of Washington. It's a pleasure to have you here, Dr. Pengelley.
Well, thank you so much. Thank you for that very nice introduction. And I'm really delighted to be here today. I'm honored to be asked to give the Kieval lecture here. And it's so nice because I feel I have a lot of friends here already. My wife and I have been visiting here over the years quite a number of times, and we absolutely love here and the area. And so it's great to be here to be able to talk with you tonight. So I'd like to sort of begin by saying a couple of prefatory things. I realize I have a very broad audience here tonight. It's really true what the announcement said, that no mathematical background should be required. There will be a few times when I'll really talk about some mathematics, and if that's a little much, you can either try to keep along, or you can take a little 30-second nap and just come back a little later, and that's fine. Because I can't talk about mathematics without actually doing some mathematics. That's in my genes or my blood or something like that. So there'll be a combination of quite a lot of history and culture and background and context and some mathematics. My own mathematical research is in algebraic topology, and I promise not to tell you another word about it tonight. But through my teaching, which the president mentioned, I've also become very involved in teaching with primary historical sources over the years. This is one of the ways in which I engage my students to work on things in advance and come to class with things to discuss. I could wax on for a long time about why I think teaching with primary sources is a really great thing in mathematics. But one of the things it does is it raises lots and lots of questions, more questions than a typical textbook does. And I think that having students grapple with questions, both in advance and in class, is a wonderful thing. And without telling you all the details, I was teaching a course in which I wanted to include some work of a woman named Sophie Germain in an honors course that I was teaching, a freshman honors course at my university. And over a period of about 17 years, off and on, I first learned that her work that was somewhat known about was not really available for me to use in teaching with my students. And I learned nonetheless that I could perhaps go and find out about her work. And so I've been doing that. And I'm now at the point actually where, after off and on work for a long time, I've actually finished writing a quite big piece of work about her work, and you can look at it much more than just during this hour if you like. You'll find it at either of these two websites, or you can just Google my name, David Pengelley, if you can spell it correctly. You'll get to my home pages, and you'll very quickly find that there's a preprint there that's basically like the title of my talk here, and you can read to your heart's content. This is something that was published in Historia Mathematica recently, but there's a preprint on my website. And the first several pages of that would be an elaboration of a lot of what I'm going to talk with you about today at the beginning of the talk, and then there's more detail about the mathematics in her manuscripts later on. So if you want more than I'm able to talk about in the next 50 minutes or so, you can read what I have there. So I'd like to spend a bit of the first part of this hour telling you who Sophie Germain was, and also what Fermat's last theorem is, and why we should be interested in those things, and why we should be interested in them together. So I'm actually going to spend a good bit of time with you just looking at this plaster bust of Sophie Germain, me telling you a bit about her life as context before talking about any mathematics at all. And then I'll tell you what Fermat's last theorem is and how she's connected with it. So who was Sophie Germain? When did she live? What did she do? She's known today as the first woman we know of in the world who did really important original mathematical research. There were women before her in the history of mathematics who were scholars, teachers, writers, but we don't know of them doing really important original research in mathematics like she did. She was born in 1776, died in 1831. As far as we know, she lived her entire life in Paris. There's actually a wonderful little book that I'd like to mention to you. I didn't write it. It was written by a woman named Dora Musilak, and it's called Sophie's Diary. So S-O-P-H-I-E', Sophie's Diary. You can get it on the web easily, and it's a fictional diary of Sophie Germain from age 13 to 17. So it encompasses the years before we really know very much about her, but it fits very nicely with what we do know about her. And it is fiction, but I find it so well written and fits so well with the facts I know that I have a hard time telling fiction from reality when I'm reading Sophie's Diary. So I recommend it to you as a really neat book. It tells how Sophie Germain self-educated herself in mathematics to university level without any apparent teaching or mentorship. And she does it while the French Revolution is happening outside her door from age 13 to 17. She lived in the center of Paris when she was 13 years old. It was 1789, and the French Revolution began. And she lived right in the center of Paris. Now, we don't know much about her personal interaction or reaction to the French Revolution, although we know a little bit. And I'll tell you a tiny bit about it. So she lived in a middle-class family. Her father was a silk merchant, and he was a little bit involved in one of the constituent assemblies during a certain portion of the period of the French Revolution. We know from someone a close friend of hers, who wrote an obituary about her shortly after she died, we know that she in part survived mentally the French Revolution that was happening outside her door by retreating into her father's personal library. And in that library, she found books like A History of Mathematics written by Montucla, and she found several more mathematics books. Even though her father wasn't in any way a mathematician, I guess he was enough of an educated man that he had a library which offered her those things. And she began to read those things and study them, not just a history of mathematics, but also some actual mathematics books. We know, for example, there was a differential calculus book written by Cousin, and we know very specifically that she studied this book in a particular year when she was still less than 18 years old. We also know for a fact that her parents tried to prevent her from studying mathematics. They did this. We don't know for how long they did it, but they did it specifically enough that we know that in order to prevent her from studying mathematics, even at night after everyone had gone to bed and they found out she was up studying mathematics, that they took away her candles, they took away her heat in her room, they took away her clothes, so that in order to try to force her to sleep at night rather than be up studying mathematics. But apparently it didn't really work, and they apparently eventually gave in and let her study mathematics on her own, which she did. Unlike other women before her who studied mathematics, we have no knowledge of any mentor or person who provided her with specific mathematical materials. We don't know more than a little bit about her father's library and what she might have managed to get in some other ways. It's extraordinary today to imagine, I find it extraordinary to imagine someone who could self-educate themselves to university level in subjects like mathematics, so that she could do what I'm about to tell you she then next did, which is so extraordinary to me that I think of it as being fact stranger than fiction, because what we do specifically know she did in 1794, when she was 18 years old, is she somehow knew, at least the family, of a male student at the École Polytechnique. Now, the École Polytechnique was the university that had been founded as a result of the French Revolution. It was the sort of first model for a modern university in which the faculty were both researchers and teachers at the same time. Prior to that, universities were mostly teaching institutions. Research was mostly done at Royal Academies of Science. And there was a student at the École Polytechnique whose name we know. His name was Antoine Auguste Leblanc. And we know that he died while he was a student at the École. And we know that at that time, professors like the top mathematicians of the age at the École Polytechnique, like Lagrange and Legendre, names that are associated with things you still read and hear about today, they would give lectures, and then at the end of But the only real interaction between them and their students, this is pretty unlike today, was that at the end of each term, the students would be invited to write something in response to the lectures that the professor had given. And we know that Lagrange was so impressed with the positive change in the comments that he was receiving from this student Leblanc, whom he didn't really know. I mean, he didn't know who Leblanc was. He just knew that he got papers by someone named Leblanc, but I guess they weren't very good. And one time, the writings from Leblanc were so good all of a sudden that Lagrange, the professor, demanded to meet with Monsieur Leblanc, the student. And it was only then that Lagrange learned that Leblanc had actually died and that somebody else had turned in papers using Leblanc's name, like forged homework, okay? So Lagrange then demanded to find out who the author of this forged homework was, and that's how he found out that a woman named Sophie Germain, we don't know exactly how this happened, who lived in Paris, had written this work. And he went to her home, and this began a very long mentorship on the part of Lagrange and also a professor named Legendre of Germain for the rest of their lives. This doesn't mean that she was immediately able to become a student at this university or even walk in the door, because as a woman, she couldn't. Women were not admitted as students to this university. And she also couldn't gain admission to the French Academy of Sciences, where many of them also were working as researchers. It did become known in Paris, though, at that time, that there was a young woman studying mathematics who was interacting with people like Lagrange and Legendre. So it wasn't secret knowledge at that point, but it wasn't terribly well known, because the next thing that we know happened is that in 1801, the foremost mathematician in the world, Carl Friedrich Gauss, who then lived in Braunschweig in Germany, published an incredible book, which is called Disquisitiones Arithmeticae, which means arithmetical investigations. And it wasn't the arithmetic that we think of today. It was what he called higher arithmetic, which was what we today call number theory. And Germain read this book of his cover to cover and wrote to him. She wrote to him in 1804. But she used this name Leblanc still, of the student who had died at the École Polytechnique. So Gauss began getting letters from a man whom he didn't know in Paris, but these letters were so interesting that Gauss, the top mathematician in the world, engaged in a correspondence that lasted for 4 years with this Leblanc, he thought. And it's pretty interesting reading. And then Sophie Germain did something that blew her cover. She had read about the purported fate of Archimedes in ancient times, 2,000 years before, who had supposedly died at the hands of a Roman soldier when a Roman army invaded the city he lived in. And she got worried that something like this might happen to Gauss when Napoleon's armies were coming into his city in Germany. And so she actually intervened through her family with a French general who had a French lieutenant go across country into Braunschweig and find Gauss and knock on his door and say to him, I'm here on behalf of Sophie Germain in Paris, and we're going to make sure that you're okay when our armies come into Braunschweig. And Gauss said, I've never heard of anybody named Sophie Germain in Paris. What are you talking about? And this is how Sophie Germain blew her own cover and then had to write to him and admit that he'd been corresponding with her rather than with this man, Leblanc. And I could read you the most amazingly awful things that scientists in the 19th century wrote about the inability of women to do science and mathematics, but I won't read you any of that. Instead, I'm going to read you a very brief quote from what Gauss wrote back to Germain after she wrote him this letter admitting who she really was. Here's a little of what he said. He wrote in 1807, he said, "But how can I describe my astonishment and admiration on seeing my esteemed correspondent, Monsieur Leblanc, metamorphosed into this celebrated person, yielding a copy so brilliant it is hard to believe. The taste for the abstract sciences in general, and above all for the mysteries of numbers, is very rare. This is not surprising, since the charms of this sublime science in all their beauty reveal themselves only to those who have the courage to fathom them. But when a woman, because of her sex, our customs and prejudices, encounters infinitely more obstacles than men in familiarizing herself with their knotty problems, yet overcomes these fetters and penetrates that which is most hidden, she doubtless has the most noble courage, extraordinary talent, and superior genius. Nothing could prove to me in a more flattering and less equivocal way that the attractions of that science, which have added so much joy to my life, are not chimerical than the favor with which you have honored it. The scientific notes with which your letters are so richly filled have given me 1,000 pleasures. I have studied them with attention, and I admire the ease with which you penetrate all branches of arithmetic and the wisdom with which you generalize and perfect." So I think she must have been pretty happy to get a response like that. Gauss was not a very friendly person. This is about the nicest thing I've ever seen that he wrote. He carried on a correspondence with her for a little more time, but then his work shifted. He became director of the astronomy observatory in Göttingen, and he really had to stop doing much mathematics for a while, and he dropped the interaction with Germain after another year or two. So Sophie Germain was already known then. It was already known in Paris through the early 18-teens for work she did on an Academy Prize problem in what's called elasticity theory. This was about how iron filings on vibrating plates would form incredible patterns as the vibrations died down. And I'm not going to tell you much about that. You can read more about it easily. But she actually she actually submitted several times and then was awarded the French Academy Prize for this elasticity problem. But it was sort of bittersweet because they said she hadn't really completely solved the problem and they wouldn't publish her work. And keep in mind, she was still completely on the outside of the university, the French Academy. She was basically working out of her home and having what interaction she could with other people. So there was this bittersweet but really rather prestigious prize that she received. And then at the same time, she was working in number theory. And she was working in number theory right from the communication with Gauss that I told you about in the 1800s. And then after this prize competition for elasticity theory finished in 1816, we know that she worked a whole lot more in number theory. And it's that work that I really want to tell you about. So she's been known for the past 200 years for having proven an important result in number theory, which is called Sophie-Germain's theorem. We know about it, and I'll show you this, because of a footnote that, not because she was able to publish it herself. She didn't publish this particular result herself, but she was credited with it by a footnote in a publication of Legendre's. And I'll show you that. But what I want to show you is that, in fact, there's much, much more that she did that we haven't known about for the past 200 years that's in her handwritten manuscripts. And that's what I want to share with you. So maybe it's time for me to let you see another slide. So the next question should be, what is Fermat's last theorem and why should we care about it? Because that's the mathematics she worked on in number theory that I want to tell you about. So here are a couple of right triangles, and I'm hoping that you might remember or have been exposed to something called the Pythagorean theorem in geometry, in Euclidean geometry, which tells us something about the relationships between the lengths of the sides in right triangles. And in fact, the geometry of the Pythagorean theorem tells us that if you have a right triangle and you look at the sides of it, and if z there, is called the hypotenuse, is the longest side, then the square of the length of the hypotenuse is actually the sum of the squares of the lengths of the other two sides. Let's check that. In this triangle here, for example, which I've labeled and claim could have sides length 3, 4, and 5. Well, we could check this against the Pythagorean theorem by going down here and asking whether the square of 3 plus the square of 4 really is the square of 5. And we find that the square of 3 is 3 times 3 is 9, the square of 4 is 4 times 4 is 16, and we add them together and we get 25. And lo and behold, that is the square of 5. And so there really is a right triangle whose sides are 3, 4, and 5. Now, if you've never thought about this before, that should seem surprising. It should seem surprising that the sides of a right triangle could all be whole number lengths instead of fractional lengths or irrational lengths or something. Why should it be that if you make a right triangle and you put whole number lengths on two of the sides, that the third side should turn out to be a whole number? That's kind of amazing. But it turns out to be true. At least here's one example, and here's another one, 5, 12, 13. Just in case you thought there was only one, I gave you another one, 5, 12, 13. And sure enough, 5 squared plus 12 squared is 13 squared. You can check it. 25 plus 144 is 169. So there's another right triangle with whole number sides, and actually there are lots of them. And when they happen, these numbers are called Pythagorean triples. So 3, 4, 5 is called a Pythagorean triple. Now, Pythagorean triples are not new. They go back to Pythagorean times, which goes back several hundred years before BCE and before Euclid. But Pythagorean triples, oops. Oh, okay. Actually, they go a long way back. This is a clay tablet from the Middle East from almost 4,000 years ago. It's called Plimpton 322, and if we could read it, which people can, some people can, we would find out that this is a long list of quite large numbers that are Pythagorean triples. So 4,000 years ago, people knew a lot about Pythagorean triples, and they were very interested in them, and we can speculate, and a lot is discussed even today about why they were very interested in these things. But these Pythagorean triples were actually completely understood and what mathematicians call classified in the work of Euclid's Elements around 300 BCE. Well, the story that I want to tell you sort of starts with Pythagorean triples. It moves next to a source by Diophantus, one of the last mathematicians of classical Greek mathematics in the 3rd century CE. He wrote a book called Arithmetike, in which he studied lots of arithmetic, interesting number theory arithmetic problems. This seems to be a Greek copy. And I want to very briefly tell you what Diophantine equations are. These are equations that are named after Diophantus, and they are equations that one might be interested in studying that are polynomial equations in whole numbers. Now, what do I mean by that? Well, let's take an example. Now, I pulled this example completely out of thin air. In fact, I made it up in order for the numbers to work out, okay, so that I could show it to you, right? So here's an equation. Now, why do I call it a Diophantine equation? Well, it's a polynomial equation because we have these unknowns x, y, and z that are raised to integer powers, and the numbers, the coefficients in front of them are whole numbers, like the 9 and the 2. So this is a Diophantine equation. And my question is, what kind of solution can we find to this Diophantine equation? Can you find whole numbers, x, y, and z, that when substituted, when put in here, would make this equation true? And as I confessed, I made it up so it would work. Okay, so I fiddled to make an equation so that this would work because they don't all work, but I made one that works. Okay, so let's try the one that I made, right? Let's try letting x be 1, y be 2, and z be 3 and see what happens. Well, gee, if I let x be 1, then I have 1 squared, the cube of 2, and then I add 9. So let's do that part. 1 squared is 1, 2 cubed is 8. 2 times 2 times 2, that's 9. Then I add another 9 and I have 18. Okay, so the left side is 18. Now let's check that against the right side. The right side is twice, now the x is 1 and the z is 3, so it's twice 1 times 3 squared. Well, that's 18 also. Congratulations, we have a Diophantine equation and we have a solution to a Diophantine equation. Now remember, I just cooked this up. You can cook them up too, okay? Now, on the other hand, some Diophantine equations are more interesting than others, okay? And this Pythagorean equation is a Diophantine equation, right? We can think of it as coming from the Pythagorean theorem, but we could also just think of it as a question about numbers. Can you find 3 numbers, x, y, and z, whole numbers, so that the square of one plus the square of another is equal to the square of the third one? Of course, the answer is yes. You know from the previous page that 3, 4, and 5 will work. And so will 5, 12, and 13. Remember, another Pythagorean triple. So we happen to know, you and I know, that this Pythagorean, this particular Diophantine equation does have solutions. In fact, they're called Pythagorean triples. So now I want to move ahead about another 1,000 years or so. I want to move ahead to the person who's really considered the founder of modern number theory, Pierre de Fermat. He lived in Toulouse in the first half of the 17th century. And, well, I wish I'd met Fermat. Absolutely incredible things that Fermat did. And what Fermat did was he started studying all kinds of questions in number theory. Think of number theory as being the interesting questions about the natural numbers that you've never asked if you've only done arithmetic. Okay? So he asked the following question. And why he asked this question, someone could say, you know, what practical application did he have in mind? My answer is, this guy just loved numbers. Okay? I mean, he did this for the pure joy of understanding what was going on with numbers. And he knew very well that there were lots of solutions to this Pythagorean triple equation. He knew there were lots of sums of squares that could give another square. And what he wondered is, could this happen with cubes? Could there be a sum of 2 cubes that would be another cube? Or another way to think of it is, can you take a cube and write it as a sum of 2 other cubes? And oh, over here, he said no. It can't happen. It actually can't happen. Now, if you think about that, he didn't just try a few numbers and say it can't happen, because how many possible numbers do we have that we could try in this equation? And the answer is infinitely many, right? I mean, we could try any natural number. By natural numbers, I just mean the counting numbers, 1, 2, 3, and so on towards infinity, right? Well, there are infinitely many different possibilities. You could try your whole life to find solutions to this equation. And Fermat said, you'll never find one, because there aren't any. Despite the fact there are infinitely many things to try, none of those infinitely many things will work. He said that. Well, he didn't just say that. He went on to ask about fourth powers. He wondered whether a fourth power could possibly be a sum of 2 other fourth powers of positive natural numbers. And he said, no, it can never happen. And you might imagine he didn't stop there. He went on and said, if I look at higher powers, even than 3 or 4, if I look at an nth power where n might be 3 or 4 or 5 or anything higher than 2, will there be a way to write an nth power as a sum of 2 other nth powers? And he said, no, it can never happen. And then he wrote what has become one of the most sort of half hilarious but most interesting things in mathematics. He was actually making notes. He was the kind of guy who wrote in his books. He was making notes in his own personal copy of this Diophantus's Arithmetica book that I showed you. And he wrote that he had a wonderful mathematical proof of what he was claiming here, that there were no solutions to these equations. But he wrote that he didn't have enough room in the margin of his book to write down this proof. And this became essentially perhaps the most famous question in mathematics for the next 350 years, because it took 350 years for mathematicians to determine whether he was right or not. Now, we believe that he didn't actually have that proof that he mentioned. We believe that he may have thought he had the proof, but there was probably a problem with it, okay? And it took 350 years for mathematicians to manage just to resolve this question. And that's why it's called Fermat's last theorem, because it took us a long time to figure it out, okay? And now you want to know, well, was he right or not? And the amazing thing is, yes, he was right. Okay, but it took 350 years, and most of modern 20th century research in mathematics, in number theory and other disciplines, were brought together, and I'm going to mention one person, but it was not just one person who solved this. It was a slew of people over a century that put this together. But this was finally proven to be true by a mathematician named Andrew Wiles in 1993, less than 20 years ago. And so this is called Fermat's last theorem. No, there are no solutions to equations like this except when the exponent is 2. Now, at the time that Germain was working, this had actually become one of the most prominent questions in mathematics. But what she didn't know, and people didn't know at that time, was that it was also one of the most difficult questions in mathematics. At the time, people thought, oh, we'll figure this out. Well, it took another 200 years after Germain for it to be figured out. She didn't know what a hard question she was working on. There's a nice little image of Fermat. Here's the frontispiece of a copy of Diophantus's Arithmetica that Fermat worked with, although this copy was actually published by Fermat's son with Fermat's marginal comments published in there as well. Here's a piece from that with the Greek and the Latin translation of the Diophantus, and down here you see Fermat's marginal comment about dividing a cube into 2 cubes and 2 quadroquadratums. What do you think a quadroquadratum is?
Fourth power.
A fourth power, that's right, a square of a square, okay? Dividing 2 quadroquadratums into 2 quadroquadratums, and he's saying, no, this can't be done. So this is his famous marginal comment, but printed up. And there's Andrew Wiles, standing at Fermat's birthplace next to a stone with Fermat's last theorem on it. He's looking happy. This was after he proved Fermat's last theorem, I think. Now I want to connect Fermat's last theorem with Sophie Germain for you. So I told you that Sophie Germain has been known for 200 years for a particular result in number theory, and it's called Sophie Germain's theorem, and it's about Fermat's last theorem, and it's a partial proof of Fermat's last theorem. Now, this slide is quite mathematical, and you can close your eyes for 30 seconds if you like. I'm not going to explain the mathematics on this slide very much right now. A little later, maybe, but not right now. I just want to give you a sense for what this theorem is that she's been known for 200 years before we go on to other things. Okay? So, this theorem of hers has to do with first taking an odd prime. A prime number, I will remind you, is a number that can't be written as a product of smaller numbers. So 6 is not a prime number because 6 can be written as the product of 2 times 3. But 7 is a prime number because you can't write 7 as a product of 2 smaller numbers. You can only write it as 7 times 1. So Sophie Germain's theorem is about taking an odd prime exponent, like 7, for example, and it then says that you need another prime number, which she called theta, a Greek letter, and I'm going to stick with that. And then there are 2 conditions that I'm not going to explain right now that this prime theta has to satisfy in relation to p. It involves something called modular arithmetic, which we're going to talk about in a little bit. And it then says that if you have a prime theta that satisfies these 2 extra conditions, then if there were a solution to the Fermat equation using the exponent p that we chose to begin with, then one of the 3 numbers x, y, or z in the solution would have to actually be divisible by the exponent number p. They would have to actually be multiples. One of them would have to be a multiple of p. Now, if you think about this, this is a partial solution to the Fermat problem because it tells you that if there were solutions to the Fermat equation, they would have to be quite restricted. They would have to be numbers that aren't divisible by p. But you notice this theorem has lots of ifs in it. If you can do this, and if you can do this, and if you can do this, then if this, then this. Okay, but this is a typical theorem in mathematics, and this is what she's been known for. And if you can do this, then you say that you've proven case 1 of Fermat's last theorem. Now, I'd like to show you where she's credited with this theorem first. This is a memoir that Adrien Marie Legendre, one of her mentors, wrote and published in 1823. And in this, he actually proves Fermat's last theorem for exponent 5. At the time, people were proving it one exponent at a time. It had been proven for exponents 3 and 4, and he proved it for exponent 5. But in there, he has a whole analysis which presents this theorem. And this is the page where he credits Sophie Germain with it. Would you like to see that in English? Okay. I've made you an English translation. Okay. And you see that in this footnote right here, right there, Legendre says, this proof, which will undoubtedly be considered very ingenious, is due to Mademoiselle Sophie Germain, who successfully practices the physical and mathematical sciences, as evinced by the prize she won from the Académie regarding the vibrations of elastic membranes. This is the exact place, the only place in the literature from which we know for sure Sophie Germain proved this theorem, which this is just the last page of. He's got several pages of this theorem, and this is actually a table showing how to apply this theorem of hers. Remember, the theorem was about prime exponents in the Fermat equation. This table actually shows how to apply the theorem to all prime exponents less than 100. You see the exponent going up to 97 there? So he's presenting all this as Germain's work. So to make a long story short, I wanted to see Germain's original work if it existed, and I wanted to, I also was not quite sure what in this treatise was hers and what was his. Even though I think he did his best to attribute to her what he thought he should, I became unclear about some things. And so with a colleague, I began looking at her manuscripts, which I managed to find existed, at least many, and get hold of. And it's an absolute miracle that her manuscripts have survived, because she had no association with a professional institution. When she died, they were probably sitting in her desk drawer at home, and they could have just completely disappeared. But they didn't. And here's one of them. So this is the first actual manuscript of hers I'm showing you. This is the first. This is the first of a beautiful 20-page manuscript that is in the French National Archives in Paris. Then page 92 is the numbering of the French archive, not Germain's. This is her. This is the first page of this treatise. You see this lovely underline here. This is the title of it. This is the first theorem. She's got it beautifully underlined here. And in fact, this is exactly the theorem that Legendre credited her with in that footnote. Here it is in her hand, in her manuscripts. And it's been sitting in the French National Archives for about 200 years, and I have no real belief that anyone seriously looked at these things until now. Now, I want to tell you about this also. This is a letter. This is the top of the letter. She wrote this letter on the 12th of May of 1819 in Paris at her home. This is a little passage out of the letter. I've put ... here, and then there's more ... and this is Sophie Germain's signature at the bottom. This is a 3- or 4-page letter, and it was written to Gauss in Göttingen, the Gauss with whom she had corresponded earlier. And she had been encouraged by someone to write to him in 1819 and tell him about her work on Fermat's last theorem, and she did that. And this letter actually summarizes all of the work she'd been doing on Fermat's last theorem over a 3- or 4-year period. It's really neat reading. And I'm going to read to you a little bit of it right now. I'm going to read to you a little bit just before this paragraph and then part of this paragraph right here. She says to Gauss, after 10 years of them not corresponding, she says, "Although I have worked for some time on the theory of vibrating surfaces, I have never ceased thinking about the theory of numbers. I will give you a sense of my absorption with this area of research by admitting to you that even without any hope of success, I still prefer it to other work which might interest me while I think about it and is sure to yield results." And then she says, "Longtemps avant que notre académie," which translates as long before our academy, proposed a prize for a proof of the impossibility of the Fermat equation, this type of challenge tormented me often. I had a vague inkling of a connection between the theory of residues and the famous equation. I believe I spoke to you of this idea a long time ago because it struck me as soon as I read your book. And she's talking about the Disquisitiones that she had read in 1800. And then she says, "Voici ce que j'ai trouvé," which means here is what I have found. And she goes on after this sentence for several pages to tell Gauss all the work that she's done to try to prove Fermat's last theorem. Now, she actually had a plan for how to prove the whole of Fermat's last theorem. Not just one exponent at a time or case one or whatever, but how to prove the theorem for all exponents. And I'm going to try to tell you a little bit about that plan, how it went. And this is where we're going to do some mathematics. But we'll come back more to some other historical aspects in a little bit. So So I want you to know about clock arithmetic, which is sometimes called modular or congruence arithmetic by mathematicians. So there's a clock. It's a familiar clock. It's got 12 numbers on it, except that I've relabeled the 12 as 0, because if you think about it, that's a better name for 12 on a clock than 0, because when you add 12 on a clock, you get back the same thing you started with. So 12 is really like 0. Well, 2 plus 3 is 5. We all believe that. But what if I say to you that 9 plus 7 is 4? You'd say, wait a minute, he's gone crazy. Okay? But I don't think I've gone crazy, because I'm working on this clock. And on this clock, 9 plus 7 is 4. You can start with 9 and count 7 on, and you'll get to 4. Why is that? It's because when you add the 9 and the 7, you could in your mind think 16 if you want. I mean, you could count with your fingers and you'll get to 4. But if you do it in your head, you'll first think 16. And then you'll think, well, what is 16 on this clock? And you think, oh, when I go past the 12, I throw away 12 and I start over. So when you throw away 12 and start over from the 16, what's left is 4. And that's why 9 plus 7 is 4 on this clock. And I congratulate you because we're doing modular or congruence arithmetic here. And you notice that I've used 3 little bars there instead of 2. That's to indicate that we're doing this special type of clock arithmetic. And so what I would say in words is I would say 9 plus 7, which is 16 in the natural numbers, is actually congruent to 4 on the clock, which is called the residue. And we say we're doing mod 12 arithmetic, because 12 is how many numbers there are in this clock. If we chose a different mod, a different number of numbers on the clock, we would get a different arithmetic. Now that you're experts at modular addition in 30 seconds or less, okay, you're ready for multiplication, right? Now you're not used to multiplying on a clock, but it works just fine, okay? Well, let's take 3 9s and add them together. Now you think that's 27, but I think it's 3, but you think it's 3 too, because you take 27 and you work on the clock, and so you throw away how many 12s? 2. Throw away 2 12s, which is 24, and you're left with 3. Good. So 3 9s is 3 on this clock, right? 3 9s is 3 on this clock. Okay, now you're experts on multiplication. Now let's do division. Well, let's take this 3 times 9 is congruent to 3 mod 12, and let's divide both sides by 3. What will I get? I divide here by 3, and I'll get the 9 back, right? I divide here by 3, and there's a 3, so when I divide by 3, I get 1, and so now I say 9 is congruent to 1 mod 12, and now you really think I've gone crazy because you don't believe that, right? You shouldn't believe that. I mean, why should you believe that 9 is congruent to 1 on this clock? It's not. So what went wrong? Well, what went wrong is I shouldn't have divided. Right? I was pushing my luck when I divided on this clock. You can see, it didn't work. It gave me lies, right? Oops. Well, why didn't it work? Well, it didn't work because if you think about division by 3, one way to think about it is that it's like multiplying by 1/3. Well, there is no 1/3 on this clock, so I shouldn't have gone doing stuff with it. But maybe on the other hand, there really is a 1/3 on this clock. It's just not called 1/3. Maybe there's a number on there that acts like it's 1/3. That's pushing it, but maybe it's true. So maybe there's a number on this clock that acts like 1/3 in the sense that it times 3 would give me 1. Then that number, I could sort of call it 1/3, and I could try multiplying by it in order to divide by 3. If this isn't too crazy for you, okay? But you can check yourself that none of the numbers on this clock, when multiplied by 3, will give 1. So none of them qualify to multiply by, to divide by 3. So division really doesn't work on this clock. So why am I still telling you about it? Because I can change the number of numbers on the clock and division will work. When will it work? It will work if the modulus, that's the number of numbers on the clock, is a prime number. And I'm going to have to ask you to take that on faith today from me, because we don't have time to go into why it's true. But you have to trust me that if the modulus on the clock is a prime number, then division always works. Now 12 wasn't prime, right? Because it can be broken down as 4 times 3. So I cannot divide on the mod 12 clock. But I could divide on a mod 7 clock, and everything would work beautifully. Trust me, okay? Now, we're ready to go back to Germain, because I'm now going to tell you something which I call Germain's basic lemma. And with this basic lemma, she had a plan to prove Fermat's last theorem, and I'm going to tell you what it was. Okay? So here's what the basic lemma says. Now, I'm not going to prove the basic lemma for you. I could. It's on one slide here, but I'm going to rush through it, and you can ask me about it later if you want to. Okay? But I'm going to tell you what the basic lemma is. So what I call Germain's basic lemma says this. It says, suppose you had a solution to the Fermat equation. Remember, she's trying to show there aren't any. So she says, suppose there were a solution to the Fermat equation, and suppose that you had another prime number, which she calls theta, and suppose that, now we're getting technical and I'm going to have to show you what this means, for which something happens, namely there's no pair of non-zero consecutive nth power residues on the mod theta clock. Then the lemma will say that one of the numbers x, y, and z is a multiple of theta. Now I'm going to ask you to take on faith this lemma without a proof, but I am going to give you a sense for this lemma by doing an example. Okay, let's check out what this really means in practice. So I'm going to pick as my example exponent for my equation 3. So we're looking at the equation x cubed plus y cubed equals z cubed. And now what we have to do is, the lemma says we need to pick another prime theta, and we need to look for whether there are non-zero consecutive nth power residues. Now we have to figure out what that means. Well, I'm going to pick as my extra prime 7, okay? And then we're supposed to figure out what the nth powers are. Well, what are the nth powers? Well, because we're working on the mod 7 clock, we actually only have to look at the powers of the numbers on the clock, and we're interested in non-zero ones. So I'm only picking 1 through 6, okay? And I have to look at their nth power residues. But remember, n is 3, so I really want the cubes of these numbers. So I'm going to take the cubes of these numbers. So here goes. 1 cubed is 1. 2 cubed is 8. Aha, I heard you say 8. So why did I write 1? Because we're on the mod 7 clock. And on the mod 7 clock, 8 is 1, right? Remember? You throw away the 7 as you go around the clock, and 8 becomes 1. Okay, good. Let's do one more. 3 cubed. So what's 3 cubed? 27, but you're on the mod 7 clock, so you go how many times away around and throw it away? 3 times around is 21. Throw that away on the mod 7 clock, and you're left with 6. That's right. So there's the 6. Now you'll trust me that I computed those correctly, okay? And then we'll take, so here now are what are called our third power residues. There they are. 116, 166. So I write them down as a little list as a multiple of 7. That's right. So you can go home now and tell your friends that tonight you learned that if there were a solution to the Fermat equation for exponent 3, then you know why one of the numbers x, y, or z would actually have to be a multiple of 7. Isn't that a cute trick? You can go home and tell people that, okay? Well, we could do another example, but rather than going, okay, I'm just going to tell you the results of another example. So I'm sticking with 3. We're going to stick with the Fermat equation for exponent 3, but now I'll choose a different prime. I'll choose 5. And we're going to then compute the cubic residues on the mod 5 clock. And well, let's just do a quick one. 1 cubed is 1, 2 cubed is 8, but on the mod 5 clock, 8 is 3. That's why I wrote 3 there. Now you have to trust me on the other ones, and that means we get to write down a list of the residues, and there they are. So now I ask you, is there a pair of consecutive cubic residues on the mod 5 clock? And the answer is yes. So since the answer is yes, what does Germain's basic lemma tell me? Nothing. That's right, it tells me nothing. It only tells me something if there's no pair of consecutive residues. So that means theta equal 5 was a bad choice. We throw it away, and we could go on to 13. So I pick another theta, and you'll trust me that I've done these computations correctly, okay? And now I ask you, are there any consecutive residues there? No. So what we now learn from the basic lemma is that if there were a solution to the Fermat equation for exponent 3, then one of the numbers x, y, or z would be divisible by 13. You can go home and tell people that too. So now you know that if there were a solution to that equation, one of the numbers would have to be divisible by 7, and one of them would have to be divisible by 13. Well, you see, she's already getting some good restrictions on a possible solution to the Fermat equation. So how can she now use this? That's what we just said. How can she now use, okay, this is where I'm skipping over the proof. There it went, gone. Okay, proof is gone, okay. Now, here's what I call her main manuscript. This is where she's telling us her plan for proving Fermat's last theorem. And I'm not going to read the French to you right now. Instead, I'm going to tell you how the basic lemma of hers will enable her to try to prove Fermat's last theorem. Okay? So remember the basic lemma. I'm just writing it for you here right now. If you had a solution to the Fermat equation, and if you have another prime theta that satisfies this condition, that there are no consecutive non-zero nth power residues modulo theta, then you tell me theta would have to divide one of the numbers x, y, or z. Now, I wonder if some of you might already see what her plan is for proving Fermat's last theorem. Okay? Here it is. Germain believed that there are infinitely many such prime numbers theta, and this would prove Fermat's last theorem. Now, why would that prove Fermat's last theorem? We stick with a particular exponent, like 3, and we look for thetas that satisfy the non-consecutivity condition. You and I found, what were they, 5 and 13, right? That forced either x, y, or z to be divisible by 5, and it forced either x, y, or z to be divisible by 13. Well, suppose she were able to go on and prove that there were infinitely many of these primes theta. We only found 2, but suppose she found that there were infinitely many of them that satisfied this lemma, this condition. What would it mean? It would mean that every one of those infinitely many primes would have to divide either the x, or the y, or the z. Now, how can you have infinitely many primes, each of which divides one of only 3 numbers? How big would those numbers x, y, and z have to be? One of them would have to be not only very big, but infinitely large, right? Because it would have to be divisible by infinitely many, increasingly large numbers. Well, that can't happen, right? So what does it mean? It means there's no solution to this Fermat equation. It would create an impossibility. That's her plan for proving Fermat's last theorem. Now, you're probably imagining that she didn't succeed with this plan, because if she had, then she proved Fermat's last theorem 350 years before Andrew Wiles. Okay? Or you might imagine that she did prove it, and it's been sitting in her manuscripts for 200 years, and now I've just discovered it. Okay? But I think if that were the case, there'd be an even bigger story. Okay? So, now what she did, I just want to show you one other thing here from this manuscript. She also has theorems and results that tell us that even if she can't find infinitely many of these auxiliary primes, and she didn't succeed in finding infinitely many auxiliary primes and proving Fermat's last theorem, okay? But she does have theorems that tell her, for example, using just these 4 auxiliary primes for exponent 5, which at that time hadn't been proven for Fermat's last theorem. She claims a theorem that says that if there were a solution to the Fermat equation, then these numbers x, y, and z would have to have at least 39 decimal digits. In other words, they would be numbers that are at least 39 digits long. Have you ever written down a 39 decimal digit number in your whole life? I mean, it's saying that if there were a solution to this equation, it would have to involve extremely large numbers. Now, today, with computers, maybe people don't think 39 decimal digits is too large, but 200 years ago, it was incredible. Now, I'm going to end with just a couple of little looks at stuff of hers. This is the end of one of her manuscripts. I just want to show you that while the manuscripts may start out extremely polished, by the time you get to the end of some of them, they are getting a little more, you see a few things scratched out, you see a few things where she's trying to squeeze stuff in. These were her private manuscripts. It's like we're peeking at her private work that was left behind when she died. And I'm amazed that that they're polished enough that I've managed to figure out as much of them as I have. And so I'd just like to end by saying that Germain really was trying to prove the whole of Fermat's last theorem. So there are a bunch of side results that came out, one of which we've known about, this Sophie-Germain theorem. Then there's this theorem on the huge size of solutions. She had an entire theory for trying to verify this non-consecutivity condition. She thought she had actually proven Fermat's last theorem for some particular exponents, like maybe 10 and 26. These were all really just fallout pieces from the big plan. And now you're wondering, could the grand plan work? Could her plan really work to prove Fermat's last theorem? If Andrew Wiles had known about it, and or had thought about it or worked on it, could he have proven Fermat's last theorem this way? Could anyone else have proven it this way? And the interesting thing is, no. We know now that this way of proving Fermat's last theorem can't work. What I mean by that is not that no one's been smart enough to figure out how to make it work. I mean, mathematicians have proven that there aren't infinitely many of these auxiliary primes theta. They don't exist. So this actually can't prove Fermat's last theorem. Fermat's last theorem is true, but you can't prove it this way. We now know that. Now, the next question you might ask is, did Germain know that? Did she learn before she died that this way of proving Fermat's last theorem can't work? And the amazing answer is yes, she did. And here is an actual part of a letter that she wrote to Legendre. It's the 3rd page of a letter in which she's actually proving to him that for exponent 3, which is exactly the one we just looked at, there aren't infinitely many auxiliary primes. So she figured this out herself eventually, after she wrote all these other manuscripts. And she wrote this letter to Legendre that recognizes that, at least for exponent 3. And I think at that point, she probably realized that she might as well stop working on this approach to Fermat's last theorem. But that's how it goes in mathematics. You can work on something for years, and if you're lucky, you get something really great out of it, and you're really happy, but you can also work at something for years, and then you don't get something great out of it. So I think I'll stop there. Thank you very much.